As promised, we will now make a short excursion to hybrid functionals. Remember, in the last module, we detected a problem with the Kohn-Sham equation. It gives the correct density, but its eigenvalues do not lead to the correct band gap. Now, the Kohn-Sham system is an auxiliary system, and you have already learned that one should not ask too much from such a system. If we go back to the example of energy levels in a box, that we try to align with those of a harmonic potential. We saw that we can align the first level by moving the box up or down, but when we tried to align another level, it came out necessarily wrong, unless, of course, we aligned that one and then the first one was wrong. For this auxiliary system, asking for 2 levels to be correct was like asking to a zero-gravity simulation chamber whether a little green woman lives on some distant planet. Now, we found a way to overcome that problem. We could align both levels by changing also the width of the box. In other words, the solution was to give more freedom to our potential. Can we use this idea to overcome the Kohn-Sham bandgap problem? How can we give more freedom to a potential? Well, we can make it non-local. It can depend on 2 space coordinates, similar to the Fock operator. Would this help us? Let us go back to the Kohn-Sham equation, which gives us the correct density. Of course, we could try to change the potential, for example with a prefactor, such that eigenvalues change. But that would certainly deteriorate the density. Instead, what about this? We add to the potential a projector on empty Kohn-Sham states multiplied by a prefactor delta G. This is a non-local potential. Therefore, the auxiliary Schrödinger equation now contains an integral. The new potential leaves the density unchanged because occupied states are not touched. But when you look at the band structure, it would shift the unoccupied bands upwards. This is sometimes called a scissor operator because it is like cutting the spectrum in 2 halves in the band gap and shifting the upper half. We can give the bottom of the conduction band at gamma a target value that would, for example, correspond to the experimental band gap. And we can reach it exactly by tuning delta. So in this simple case, we see that we can find a non-local potential that gives the correct density and the correct gap. Now, let us see how this links to hybrid functionals and the use that is often made of these functionals to get closer to experimental gaps. The important ingredient of hybrid functionals is the exact form of the exchange energy. It is the Fock exchange, a double integral over 2 density matrices and the Coulomb interaction. Writing the exchange contribution in this way has the enormous advantage of avoiding the approximation of the large exchange term. For example, approximating the exchange term is the source of spurious interaction of an electron with itself, the so-called self-interaction. In hybrid functionals, we take a fraction of this exact exchange and mix it with a portion of our favorite approximate explicit density functional, such as LDA or GGA, tuned with the parameter alpha. From this, we can hope to get a better Kohn-Sham potential. We only have to take the derivative with respect to the density. This leads to a local hybrid Kohn-Sham potential. Let me just mention that there is also a tight link to so-called optimized effective potential methods called OEP. You can find more about this in the lecture notes. But in any case, you realize that here the only thing we have achieved is to get, hopefully, a better Kohn-Sham potential. Still, no more degrees of freedom, no reason to get better band gaps. What we have to do is to change the scheme by deriving a non-local potential. Again, I refer to the lecture notes for details, but you can imagine the way to go. We can make use of the fact that our exchange term depends explicitly on the density matrix. This density matrix is a non-interacting one, and it comes self-consistently from our Kohn-Sham system. But this is now a generalized Kohn-Sham system because it has a non-local potential. You can find more about the generalized Kohn-Sham system in the reference. Clearly, the generalized Kohn-Sham system with its non-local potential is what we have been looking for. Indeed, the freedom it has to yield better gaps is one of the reasons for its success. This also explains why there are today so many kinds of hybrid functionals. You can start the series, for example, with PBE0, a functional by Perdue, Burke, and Ernzerhoff. It is a simple mixture of factors 1/4 and 3/4. Very popular are also hybrids of the Heitz-Kusaria-Ernzerhoff family, for which you can find some basics in this reference. They contain an additional parameter that you can link to screening. All these hybrids indeed have parameters, and today there is a lot of tuning going on in order to obtain gaps or also optical spectra with reasonable effort. You can look, as an example, at this reference of Leo Kronig and co-workers. Really good results are obtained, but I will not show you tons of values for band gaps. Rather, keep in mind the following. We have given our auxiliary potential more freedom, and therefore, we could get a better description of more observables. We have done this by going from Kohn-Sham to generalized Kohn-Sham with a non-local potential. Finally, as an outlook, there is a strong link between hybrid functionals and screened Hartree-Fock. Screened Hartree-Fock, in turn, can be seen as an approximation to many-body perturbation theory. So hybrids, in a way, act as a rough approximation to the widely used GW approximation of many-body perturbation theory. But this is another story.